this, and she's actually here. She's actually here at EPFL for still another few weeks. She's spending part of her sabbatical here. The other part she spent in Japan previously. So yeah, please go ahead. And next.
Yeah, thank you, Christopher, for the introduction and also for hosting my visit at EPFL. And thank you for getting me connected with Marvel so I can share with you my research today. So I would like to ask two questions to get started. Like, why are we interested in thermal transport? And why are we particularly talking about phonons? So since we are talking about energy applications, I want to point out how thermal transport is important to energy production and consumption. So for energy production, thermal transport impacts nearly every step along the process. As one form of energy, heat can be converted to other forms of energy, and a better understanding of thermal transport is important to improve the energy conversion efficiency. We are particularly interested in the direct conversion of heat into electricity. For future grid, it needs to adapt the integration of the renewable energy resources. And so that requires a faster triggering at the higher voltage and current for improved grid control and protection. For the power electronics that serves as these fast dynamic interfaces, they are currently similarly limited. For thermal energy storage or hydrogen storage, thermal transport directly affects the charging and the discharging rate, and thus the efficiency of the energy storage systems. For energy consumption, thermal transport touches different sectors, and I'm going to just give two examples here. Overheating cripples the operation of microelectronics. The external cooling loops create giant carbon footprints and cost billions of US dollars yearly. If we could have a better way to dissipate heat from the cheap hotspot, that can be translated to large energy saving. For building decarbonization, one of the goals is to use properly thermally insulated structures to save the energy consumption for heating and cooling, because over 50% of the energy consumption at residential sites are used for heating and cooling. For some of these applications, we wanted the thermal conductivity K to be as low as possible to create a larger temperature gradient and reduce heat loss. Some other applications, we want the thermal conductivity K to be as high as possible to create efficient heat dissipation pathways. There are also applications where we want the thermal conductivity to be controllable. So how to engineer materials and devices to achieve desired thermal conductivity? We need to fundamentally understand the thermal transport processes. So in today's talk, I'm mainly going to cover the applications for energy conversion and the thermal management of electronics. Now, why phonons? Phonons are the quanta of a lattice vibration. So they are the major heat carriers in semiconductors and insulators. The properties of those phonons directly determine the thermal conductivity, which is a function of specific heat, how much heat a phonon carries, group velocity, how fast a phonon travels, and mean free path, how far a phonon travels before it collides with other phonons or impurities. Because mean free path is the product of group velocity and the lifetime, so we can also write this equation in terms of lifetime. I want to draw your attention to this summation sign I here. So the thermal conductivity essentially is this accumulative contribution from different phonon modes. So instead of just looking at one single number k, we do want to dive deeper to get the microscopic picture of how different phonon modes contribute to the thermal conductivity. For example, for a long time, we use a single number of mean-free paths to describe the average distance phonon travels in a single material. That was 34 nanometer for silicon. But with the help of the detailed DFT-based calculation, we were able to map out the mean-free path distribution in different materials. As you can see, the mean-free path distribution spans several orders of magnitude from nanometers to microns. And in different materials, they have a different distribution that becomes the guidelines for nanostructuring to reduce the thermal conductivity for some electric applications. One critical piece of information of phonon dynamics is the phonon dispersion curve, which is a relation between the frequency omega and the wave vector k. So for a solid with more than 2 atoms in the primitive cell, there are 2 types of phonon modes: acoustic mode, which involves the mass center movement, and optical modes, which involves the internal vibration. So typically, optical modes have higher frequency. The slope of the dispersion curve gives you the group velocity. So you can see acoustic modes typically have higher group velocity. So just keep this in mind, and we are going to revisit the phonon dispersion later in the talk. In my group, we combine modeling and experiments to study some of phonon transport. On the modeling side, we have been heavily focused on the nanoscale modeling, including DFT calculation, molecular dynamics, atomistic Green's function. And at mesoscale, we are doing the Monte Carlo simulations and the finite element at the macro scale. And for experiments, we have 2 custom-built setup in our lab to do the laser-based palm probe technique. And this gives us the opportunity, this capability to measure thermal conductivity cross-plane and in-plane for nanostructured materials. We're also doing a lot of inelastic X-ray scattering at national labs. We started doing synthesis about 2 years ago, mainly focused on the polymer nanocomposites. So this allows us to look into some phonon transport in a variety of materials for energy applications and beyond. In today's talk, I'm going to introduce those highlighted techniques. So I'm going to share with you our work in these 2 categories. I use the green color to denote experimental work, and the orange color denotes computational work. And you can see there's a combination of computational and experimental work. So let me start with the first part on the thermal management. Today's transistors could run faster if they are not getting so hot. The clock rate of our laptops have not been improved much since 2005 because of the heat death. In US, the government is investing $280 billion for this CHIP Act to develop semiconductors. So essentially, from my perspective, what my group can contribute is to move the thermally limited electronics to thermally managed electronics. If we zoom in, we want the thermal conductivity of the cooling substrate to be as high as possible. And we also want the interfaces to have a high conductance. So this way we would have a very smooth heat conduction pathway. So I'm going to share with you 2 examples of our efforts towards the high thermal conductivity material and thermal interfaces. Back in 2013, there was this paper published in PRL predicted the ultra high thermal conductivity of cubic boron arsenide. And this drew a lot of attention in the community because the thermal conductivity become comparable to the best semiconductor diamond. And the reason for the ultra-high thermal conductivity was attributed to the two features in the phonon dispersion. So if we compare boron arsenide in black with silicon in red, we can see there is a large acoustic and optical gap that limits the scattering between acoustic and optical phonons. And the three acoustic branches are close to each other, the so-called acoustic bunching. So that limits the acoustic phonon scattering. So essentially, this limits the three phonon scattering process and gives the high thermal conductivity. But 2 years later, the experimental work showed only 200 watt per meter Kelvin, which is 1 order of magnitude lower. This large discrepancy begs the question, was the calculation inaccurate, or was the sample not pure enough, so it contains defects causing extrinsic scattering mechanisms lowering the thermal conductivity? Now, to answer this question, we decided to experimentally measure the phonon dispersion to see whether we can see those two key features. To measure the phonon dispersion, there are two popular methods, the inelastic neutron scattering and inelastic X-ray scattering. They have their own pros and cons, and I'm going to show you the reason we chose inelastic X-ray for this particular study. Typically, neutron scattering requires much larger sample size, an order of a millimeter cube. But with X-ray, you can go with much smaller sample size. This can be particularly useful if it's hard to grow high quality, large single crystals. And that is the case here. So we chose the X-ray scattering for the phonon dispersion of cubic boron arsenide. We worked with collaborators at Oak Ridge National Lab. They synthesized the boron arsenide single crystals using the vapor transport techniques, and they did the XRD and the EDX. All looks good. We took the sample and we did the single crystal XRD screening. And unfortunately, we couldn't really find one sample which has a single domain. So we're quite stuck. And then I said, how about we break down into smaller pieces? And luckily, we were able to identify one small piece out of sample 3, which gives us the majority of a single domain. And the sample dimension is suitable for the X-ray measurements. So very briefly, the inelastic X-ray scattering is a photon in and photon out spectroscopy. By monitoring the energy and the momentum change of photon, we can extract the frequency and wave vector of phonon. So we do this for different wave vectors, and then we can map out the phonon dispersion. We carried out the measurements at Oregon National Lab in the transmission geometry. So this is how a typical energy scan looks like. We have those circles that's from our measured data. And so in the center, we have the elastic peak. And on the two sides, we have this phonon annihilation and the phonon creation. So from these peak positions, we will get to the phonon frequency, and the inverse of the peak width gives us the phonon lifetime. So our key results are summarized here. The measured phonon dispersion marked in blue agreed pretty well with the calculated dispersion in red, and also agreed with the Raman measurement from a previous study. So from here we can see we did observe the two features that is important for the ultra-high thermal conductivity. So back in 2016, we concluded that this material should have ultra-high thermal conductivity if the high-quality single crystal samples can be made for the thermal conductivity measurements. 2 years later, 3 papers published in Science and confirming the ultra-high thermal conductivity of this material. So now let me switch gear a bit to talk about interfaces. When I first started looking at interfaces as a graduate student, I kind of like start marking out the pros and cons of different modeling techniques. And I noticed like this atomistic green function is a very powerful technique, except it couldn't include the unharmonicity. So when I was a graduate student, I mainly worked under the harmonic framework and included the first principles for force constant into the AGF framework for 3D interfaces. And now when I started as a faculty, I wanted to change this question mark into a check mark. So we worked on this problem, and I'm going to share with you what we are getting there. Very brief summary of this atomistic green function method. So typically, like when you have a system, this is kind of infinitely large system, you partition it into 3 parts. You put the physical interface in the center region. And the retarded green function describes the dynamics of phonons in the center region by taking into account the effects of the left and right needs through the self-energy terms, the sigma L and the sigma R. And with that, we can write out the transmission function and then calculate the heat current and the thermal conductance using Landau's formalism. Very detailed derivation can be found in Mingo's paper and Tim Fisher's paper. Those 2 papers I read many times. And so when Mingo first introduced this atomistic green function in the harmonic framework, it was for this 1D structure. It wasn't that challenging to extend it to the 3D structure. Mingo also introduced a framework for the 1D atomic chain in terms of including a harmonicity. But to go from this 1D unharmonic to 3D unharmonic, it's significantly more challenging. There were different efforts to extend it to 3D, but different levels of assumption were made. So we want to really look at this problem by developing a rigorous formalism where we can include the first principle force constant for both second order and third order into a framework to accurately describe the phonon scattering at the interface. When we looked deep into this problem, we realized one main challenge comes from the third order tensor. You couldn't really see any pattern, and it's very large tensor. So in the real space, it depends on the 3 vectors in the real space. And so we tried to reduce this computational load by introducing a new Fourier decomposition method. With this, we were able to convert this problem into the reciprocal space, and it only depends on 2 wave vectors in the reciprocal space. So it dramatically reduced the otherwise prohibited computational load and allow us to include the third order force constant into the framework. So we now revisit this retarded green function. Now you notice here I have one extra term compared to the harmonic green function. This is a many body self-energy term, which essentially describes the phonon scattering. And we need to calculate this many body self-energy iteratively. We reformulated everything in the reciprocal space. So by solving this many bodies of energy iteratively, we are able to include the inelastic X-ray, inelastic scattering effect. One example here is for the single silicon germanium interface. If we only have the harmonic contribution, so basically only for the phonon frequencies which are overlapped between silicon and germanium, we can have the phonon propagation that is marked here in pink. But with the inelastic scattering, where we allow 3 phonon scattering to happen at the interface, we can access some of the phonons where the density of states don't overlap between silicon and germanium, because its inelastic scattering opens up extra channels at the interface. And that needs to enhance thermal interface conductance compared to the harmonic case. So we are very proud to come back to this table and put a check mark there. And with this new development, we are also able to discover this new intrinsic thermal interface rectification in the quantum region. So essentially, we discovered like if in the quantum region, the phonon populations follows the Bose-Einstein distribution. So as you flip the direction of your heat flow, the phonon populations would change on both sides. Now, with the interplay of the inelastic scattering, we're able to see the nonlinearity happens at the interface that creates the thermal rectification. The details can be found in our new publication here. So as we're talking about the thermal rectification, I want to introduce another work in more details. It's a tapered ball brush. So we are familiar with the electronic diode, which allows electric current to travel in one direction, but not another. And that's the building block of today's information technology. What if we have thermal diode where heat can travel preferentially in one direction? In that case, we can imagine inserting the thermal diodes in the building envelope. In a tropical country, we can put the thermal diode in a way where we only allow heat to escape from the building. In a cold country, we can flip the direction of the diode to only allow heat to travel into the building. That can potentially lead to energy saving for heating and cooling needs. We can also imagine for hydrogen storage, if we introduce the thermal diode, then we could have this on-demand control of the hydrogen release. So we looked into the polymers for the potential thermal diode behavior. So people studied this asymmetric carbon nanocorn, asymmetric graphene nanoribbons before, but I wonder if we can also observe this thermal rectification effect in polymers. So particularly we looked into this tapered broad wash polymers, which has this highly extended backbone. Here we use polynolpulin, and stabilized by the side chain here is polystyrene. So the side chain length is systematically varied to form this cone shape. And we fix both ends and introduce a heat reservoir to record the heat current in the forward direction. Then we flip the directions, flip the heat reservoirs to record the heat current in the backward direction. Very surprisingly, we got the backward heat current to be larger. This is opposite to what people observed in asymmetric carbon nano-based materials, where they typically observe from wide end to narrow end, you have a higher heat current. So we spent quite some time figuring out what's going on, why we're getting this backward heat current being larger. And finally, we found like there is this structural disorder transition from the more disordered wide end to less disordered narrow end. That leads to different temperature dependence of the thermal conductivity. So if we are looking at the forward heat current, we are looking at the thermal conductivity of the narrow end here for the lower temperature, and the thermal conductivity of the wide end for higher temperature. But then if we flip the direction, we're looking at this 2K minus there. So the two reds are pretty much similar. So we compare the two blues, the backward thermal conductivity is higher. That explains why we're having the backward heat current being higher. Then we define this thermal rectification ratio and calculate it as a function of device length. And we see this significant increase in trend with the device length. So now if I take a step back and re-share with you is for the thermal conductivity equation. So we have the thermal conductivity as function of the mean free path. In the diffusive picture, the intrinsic phonon mean free path is much smaller than the system size. So the phonons that get scattered inside, they don't really sense much of the existence of the boundaries. So you get a thermal conductivity, it's pretty much just one single number. That's what we typically encounter. But as the system size goes down and become comparable to the mean free path of the phonons, then the phonons will get strongly scattered at the boundaries, and that effectively reduce the overall mean free path. So the thermal conductivity would increase linearly with the system size in this ballistic region. Now, with these signatures of thermal conductivity dependence for these two regimes in mind, let's replot the thermal conductivity in the forward and backward direction. We can see in the forward direction, we clearly see this ballistic signature and the diffusive signature for the backward, for the forward direction. Sorry, I said it wrong. So in the backward direction is ballistic, and the forward direction is the diffusive. So if we take a look at the schematic, essentially our understanding is when heat propagates into a system through this highly disordered white end, they would get into this side chain, and then essentially through this very weak van der Waals interactions, they have a very short mean free path. But then if we have the heat travels into a system from the highly ordered narrow end, majority of the heat will go through this ordered backbone and propagate through the the strongly bonded carbon-carbon covalent bonds. So in this case, we're demonstrating in the first time, the heat transfer enters the two different regimes by simply flipping the direction of heat current in the same system. So we're hoping to look more into other polymer-based thermal diodes. Now let me switch a gear to talk about the energy conversion. So over half of the heat is rejected as waste heat. If we could harness even 10%, that can be a large energy source. Thermoelectrics can directly convert the temperature gradient into electricity. So when you apply the temperature gradient onto thermoelectric materials, the charge carriers will diffuse from hot to cold side, creating a voltage. If you connect this into a circuit, you will get a current flowing through. This is one example where the temperature gradient creates the current and lights up the group name, like my group name, my name initial, and the figure of merit for thermoelectrics, ZT. So ZT essentially depends on three material parameters: a Seebeck coefficient, electric conductivity, and the thermal conductivity. So we wanted the thermal conductivity to be as low as possible to get a higher ZT value, because a higher ZT value would be directly related to a higher energy conversion efficiency. Now, another example I want to give here is the hot carrier solar cells. This is considered as a third generation solar cells. They are predicted to outperform the other generations and potentially to exceed the Shockley-Queisser limit. The idea is like you harness those highly energetic carriers before they thermalize into phonons, so you get this extra gain. Now, to make that happen, we need to have a slower carrier cooling and thus lower thermal conductivity. Hybrid perovskites become very popular in the solar cell community because of the high energy conversion efficiency. It also showed extraordinary seepage coefficient, which is 1 order of magnitude higher than the inorganic thermoelectrics. Now, if I look at the thermal conductivity, it's very low, so as desirable for thermoelectric applications. The thermal conductivity is between 0.2 to 0.5. It's kind of comparable to amorphous polymers. So I start to wonder why this well-structured crystalline material have comparable thermal conductivity with these very disordered polymers. And then we look into literature, and we identified like 3 hybrid perovskites as representative materials to represent the different dimensionality of the inorganic groups. And then we look into literature. At that time, when we started this project, the only literature study we could find would be these 2 calculations on the methylammonium net iodide. As you can see, there's clear difference between those 2 calculations. And for the other 2 material, we didn't find anything. We actually performed the calculation ourselves on the second material, and we saw this very negative frequencies indicating the unstable structure. And so we said, okay, how about let's measure the phonon dispersion to provide some benchmark for those materials. As I mentioned, like the size could be of concern for the previous study of boron arsenide, but it's not so much of a concern for this hybrid perovskites because people can make large enough sample. But the other concern is this incoherent hydrogen cross-section in neutron. If we do a neutron scattering, basically this huge signal from hydrogen would mask the signals from the other elements. We are most interested in the acoustic modes, which are dominated by the heavier elements. So if we are going to go with the neutron scattering, we need to replace hydrogen atom with the deuterium. So the easier way is just go with X-ray. So that's why we decided to use X-ray again for this study. Our key results are summarized here in terms of the phonon dispersion of the first 2 materials. Those lower branches are the acoustic modes, and higher branches, those markers, the blue markers, are optical modes. Now, if I bring back the thermal conductivity equation I introduced earlier, one thing we can see is there is no gap between the acoustic and optical modes, which is opposite to the boron arsenide case. So here, we would expect the strong acoustic optical scattering that leads to a small lifetime. And second thing I want to point out is the acoustic modes are very soft, meaning the frequency range of the acoustic modes are very small. Why do I say that? So you can see this only goes up to 1 terahertz, or the other case, it only goes up to 0.7 terahertz. If I bring this net telluride as a reference, it shares the same heavy element net, but you can see the acoustic modes goes up to about 3 terahertz. So these soft modes wouldn't give the small slope and small groove velocity. In this case, we would expect even smaller groove velocity. So without even measuring the thermal conductivity, we already predicted the thermal conductivity of the second material will be even lower. And we did confirm that by performing the measurements. Now, the difference between those 2 materials can be seen from the structures. So in the first case, we have this corner sharing octahedron forming the 3D continuous framework. And those organic components just sit in the cage. And in the second case, those phase sharing octahedron forming the isolated dimers So there's no continuous framework that gives even weaker interactions. And then we start looking into 2D hybrid perovskites. As we were wrapping up our results, we noticed there were publications in the community, meaning these type of materials are really gaining attention in the community. But one thing we noticed was only cross-plane semiconductivities were reported by the reflectance measurements. So we wonder whether we can obtain the in-plane semiconductivity using our transient thermal grating technique. Very briefly, we have this pump laser here, and we split into 2 beams. And these 2 pump beams would cross in the sample. The interference of the pump beams will create this periodically varying temperature profile, so-called thermal grating. Then we use a probe beam to detect how quickly the grating decays. By monitoring the diffracted probe beam, we can extract the thermal diffusivity. And then this diffracted beam is very weak, so we send in another reference beam to enhance the signal, and as well as get rid of the unwanted displacement signal. So 2 advantages of this technique. First, the heat transfer distance is well defined. It's from the peak to the knob of the thermal grating. And we have the capability to vary this grating period by changing the angle. And that can give us the opportunity to go to the quasi-ballistic regime. And the second advantage is we don't need any transducer layer as a typical reflectance measurement. So we don't need to consider this interface between the transducer and the sample. So with that, we're able to perform the first measurement of the in-plane semiconductivity of a hybrid perovskites. And this can also be used to measure polymer solutions, where we demonstrated this for the thermoresponsive polymers, where we can see the the fast semiconductivity change across the lower critical solution temperature. It can be used to measure polymer thin films, where we measured the supramolecular thin films and observed the thermal percolation behavior at a lower concentration. So coming back to the 2D hybrids, we obtained the samples from 2 independent groups just to cross-check our results. So when we did the measurement on the 2 sets of samples, we got pretty much the same semiconductivity for the in-plane direction. It's about 0.28, 0.29. We did a molecular dynamics simulation. We got a pretty much a good agreement for the in-plane direction. And we took the semiconductivity data from Patrick Hopkins' group and also compared with our molecular dynamics simulation results. They agree pretty well with each other. Now, to put this in context with other layered structures, we plotted the anisotropic ratio versus the semiconductivity of the 2D hybrid with other layered material. So we can see it really go towards the lower left corner, meaning the semiconductivity is ultra low and it's pretty much approaching the isotropic limit. Now, to understand this better, we also did the inelastic X-ray scattering. Those markers are from our X-ray. And we did the MD simulation to map out the dispersion. And so if we think about the good velocity, essentially depends on the strength of the interatomic interactions. So for this structure, it has the organic chains preferentially aligned in the vertical direction. So along the organic chain is this carbon-carbon bonding, which is pretty strong. But between the organic chains and between the organic and inorganic interface is pretty weak bonding. Now for the in-plane direction, along the inorganic layer, it has pretty strong lead iodide bonding. But along the inorganic layer, it's pretty weak van der Waals interaction. So all these kind of come into play and compensate with each other and gives us a pretty much a similar good velocity for the in-plane and cross-plane interaction. For the lifetime, you can see there is this continuous key conduction path along the inorganic layers for the in-plane interaction, but not so for the cross-plane. So for cross-plane, it gets interrupted by the strong scattering at the inorganic-organic interface and also between the organic chains. So that gives a larger in-plane lifetime. That can also be seen from this left plot. We can see from the gamma to Z direction, that is the cross-plane direction, the calculated spectral energy is more blurry. So that indicates the lifetime is smaller in the cross-plane direction. So with this, we were able to really look deeper into the ultra-low thermal conductivity of hybrids and this very low anisotropic ratio of the 2D hybrids. After bringing all those complicated structures to the Argonne National Lab, the scientist finally said to me, Zhiting, can you bring a simpler crystal next time? And I said, yes. So we brought germanium telluride, and we even heated up to the cubic phase. And that's even simpler structure to look at. So the motivation, one of the motivations was from this thermoelectric applications. We can see the cubic germanium telluride shows pretty high ZT values. In this material has also been studied for the phase change applications. And so we look into literature for the thermal conductivity. So we see, okay, before the phase transition, it seems like the previous calculation were able to pretty much capture the experimental trend, but not so much for above the phase transition. So we wonder whether we can do a better job in terms of the computation to really close this gap. Now, I'm going to very briefly introduce the first principles, lattice dynamics. We started with density functional theory calculations at 0 Kelvin. Essentially, we just converting this interacting system to a non-interacting system by looking at the interaction between one electron and the mean field. And that allow us to efficiently calculate the electronic band structure and the forces between atoms. So you look at the interatomic potential, it has a harmonic and unharmonic part corresponding to the second order and the higher order force constants. So the second order force constants gives us the phonon frequency, velocity, and the high, next say the third order would give us the 3 phonons scattering lifetime. Now, because the lifetime is most difficult quantity to obtain, so let me elaborate a little bit here. In a 3 phonon scattering process, 1 phonon can split into 2 or 2 can combine into 1. Now, by choosing just 1 phonon mode, we can screen all the other modes which satisfies the scattering conditions by looking into the energy and momentum conservation rules. And then we use the Fermi's golden rule to evaluate how often those scattering happens to calculate the scattering rate, and then we can obtain the lifetime. And then we can combine this into the thermal conductivity, and then that is what we started doing a decade ago. And it showed great success in capturing the thermal conductivity behavior of a lot of inorganic crystals. But now we probably need to consider a little bit more in this case, because we are talking about the high temperature behavior, then the 4 phonon scattering can become important, and that would affect the overall lifetime. And the third order and the fourth order force constant can also renormalize the frequency. and ships the frequency obtained from the harmonic calculation. And since the DFT calculation we did was at 0K, it's not suitable for those higher temperature phases. And also, we traditionally only consider like the different phonon branches are independent. They don't really tunnel to each other. So with those three constraints, we want to make some advancements by looking at the high temperature phase, including full phonon scattering, and considering this off-diagonal term interactions. Luckily, we don't really need to start from scratch because people have been making a lot of progress in the community. So we can see those separate progress along each of them. Now, to combine them together, if we want to combine the first two, it's computationally very expensive. So our solution is to use machine learning temperature-dependent potential to significantly accelerate that process. Now, to include this four phonon scattering and considering these off-diagonal term contributions, it was not included in the original unified theory framework. So we need to modify the unified theory to include the four phonon scattering. So that's basically we included those scattering terms for the four phonon scattering. And another contribution we made was to make this unified theory compatible with the frozen phonon framework. So with that, let's first take a look at phonon dispersion. We measured those markers using inelastic X-ray scattering, and our calculation is in blue. So you can see this phonon dispersion agree pretty well. And then we look at the lifetime. So if we only consider three phonon scattering, it significantly overestimate the phonon lifetime compared to the measured lifetime, especially between this 1 and 4 terahertz range. Now, if we put everything together for semiconductivity as a function of temperature, we can see if we only include the three phonon scattering, we're here in the pink. And then if we include the four phonon scattering, we are coming down into this experimental window. We also considered this quantum tunneling effects, but the contribution is very small. So it only kind of like moved up the semiconductivity a little bit. But with that, we are able to bring the calculated semiconductivity within the experimental range. So traditionally, we were doing this 0K calculation for three phonon and only considering the diagonal term, meaning that we don't consider any tunneling between branches. But with this machine learning enabled approach, we're able to rigorously include all the three effects. So this work also provides this general blueprint for high efficient computation of the materials at the high temperature phase. With that, I would like to briefly summarize what I talked about today and to acknowledge my group. These are my students who did all the hard work, and my collaborators and the funding sources. Thank you all for your attention. Happy to take any questions.
Yeah, good. Yeah, so the talk is open for questions. So we have already some on Zoom, so maybe I can start with that. So there is one from Kile Haas. So I don't know if you want to speak up, Kile. If not, I will read your question, but maybe if it's maybe easier if you can ask it. But if not, I will, yeah, maybe I will read it. So the question was about the thermal diode with a polymer brush. And he was asking, why is it that if you go ballistic on one side, why doesn't it eventually also go into the diffusium regime on the other side? And the next part of the question was also Yeah, I mean, why is in the end is this ballistic? Because you always launch from the backbone. So why is it that you, in one direction, feel more the diffusing regime, and in the other you don't? I guess that's the meaning of the question.
Okay.
As far as I understand it.
Yeah, thank you for the question. So I will answer this by two parts. First, if we look at the heat transfer into the system from the wide end, the backbone only take up a tiny amount. It's just that chain end, but the majority is the wide and this is a non-side chain. So the majority of the heat will get into the side chain. But from the narrow end, like when you first enter, there is no side chain, and then it's a very short side chain, so it's directly go to the side, the backbone. And the reason we are not seeing the ballistic behavior converge to diffusive for the backward direction is because we haven't done long enough. Due to the limitation of the computational resources, we kind of like only goes up to like a tens of nanometers. But then essentially what I imagine, if we do long enough backbone, it will converge to the diffusive region.
Also here in the room.
So towards the end, I think also, sorry, forgotten how this works. So you mentioned the effect of high temperature, but also for phonons. If you can go back a few slides. Yeah, exactly. So the high temperature is in some ways also the same thing as the four phonons, because it's not an electronic temperature that you're talking about in the first slide. It's an ionic temperature, correct?
Yeah, so the way we kind of like look at the temperature is we are kind of like doing this self-consistent phonon approach. So we basically, we first get some normal modes, and then we populate those phonon modes to satisfy the temperature we want.
Yeah, but in some ways that takes into account an harmonicity and three phonons and four phonons, renormalizing, say, second derivatives of the free energy rather than second derivatives of the energy. So I wonder how can you put together, there's a approach. This is the scale, I suppose. I mean, so the approach of the first reference of Hellman with the four phonons, because they're also the first approach takes into account third order and fourth order terms.
So which one consider the fourth order?
So the Hellman, I think it's called Skyled. How is it called? The first reference.
The first reference.
Yeah.
That didn't consider the fourth order.
I think it includes it because it's sampling the full anharmonicity of the free energy.
Okay. So what I mean is like where, like, in addition to just have this temperature potential, and then we calculate the force constants, and we come back to the equation here. For example, like in our case, we can easily fit up to, say, 6th order or even higher order potential we want. But to consider the contributions of the, say, 4th order, we cannot come back here. We fit the forces and the displacement to extract the 3rd order and the 4th order force constants. And then we use the Boltzmann transport equation to calculate the thermal conductivity.
Yeah, now I think I understand. It seems it mixes a number of diagrams somehow in what you do, because the first reference is trying to do second derivatives of the free energies, I suppose. Okay, maybe we discuss it a bit more.
Yeah, certainly.
Okay, thanks.
Yeah.
I can also read one online question by Enrico. So Enrico is asking, again with this polymer brush, do you see signatures of the intermediate regime of hydrodynamic transport between the ballistic and diffusive? Because you see these two, you say that in one direction is ballistic and then it's diffusive. So Enrico is asking that there could be intermediate hydrodynamic regime, and would this play a role also in these systems?
That's an interesting question. We haven't thought about it, but we can think about it. Yeah.
Okay. Thanks for the talk. So I have a question about this for the decomposition method you used to sort of reduce the dimension in that question. So I'm wondering if it's do you think it's applicable on other similar questions, or it's specific to that particular case? Yeah. Because I would imagine there are many situations where you want to reduce the dimension, right?
So I think the message is quite general. Like we introduce this P matrix. So I think it should be applicable to other cases where you have this complicated tensor, you want to reduce the dimension in the reciprocal space. Yeah.
And I'm wondering, so practically if you have any open source package for that, or it's the method is still in-house?
Question. So currently still in-house, but I'm urging my students to make it like open source, so more people can use it. So we'll see like how quickly we can get this done. Yeah.
Yeah, maybe one last question on the interface. So there you have basically a semi-infinite silicon or whatever, germanium on one side that is all elastic and ballistic. And then you have the inelastic scattering only in the region of the interface, correct? But I mean, at the end, this would be relevant somehow at very, very low temperatures, because also the leads would be, say, inelastic at room temperature. So I was wondering, why maybe not do supercells with different thickness to try to keep all the inelastic effects, both of the interface and of the bulk, and try to extract the interface resistance from those calculations at various thicknesses.
So when you say supercell, are you thinking to put supercell in this framework or use a different approach?
No, just using a standard approach with third order derivatives and periodic repetition of the interface.
Mm-hmm. Okay, that's a great question. Certainly there is a limitation in terms of including the leads, the inharmonicity of the leads in the framework, because we just don't see a very clear path forward to include that into this framework. And in terms of like if you just do this supercell, maybe creating the super lattices, and then you do the thermal conductivity calculation, I would say there could be kind of like two potential concerns. First is like if you create these super lattices, you might create this coherent effect. So what we are getting would not be just a single interface effect, but because of the coherent phonon transport, you might get much lower thermal conductivity, interface conductance than the single interface. And the second thing is like the extrapolation. We might need to consider the size effect of the individual layers as well, because if you use a small or thin layers, the thermal conductivity will not be the same as the bulk. So I think those two things also needs to be taken into account. Yeah.
I have a question on the last part on GTE. So you say that you fit the potential up to a Taylor expansion to get into your force constant, the effect of temperature. But if you imagine to go to an infinite series, so to have all the possible anharmonic terms, so to expand this series at infinite, this doesn't depend anymore on temperature. So it seems a bit contradicting the fact that the more terms you add in your anharmonic expansion, the less they depend on temperature. So the phonons also that you get, even the harmonic expansion, depend on successive terms that you include in this expansion. So how does the things get into?
So may I just ask a clarification?
Yeah.
So why, when you include infinite terms for the harmonicity, it does not depend on temperature
Because
anymore?
it's the exact Taylor expansion around the harmonic point. Now, if you take the real Born-Oppenheimer energy landscape, you expand up to infinite order in the Taylor expansion, you get the exact potential, which is always the same and doesn't depend anymore on the temperature.
But if I think about it for the molecular dynamic simulations, it always includes the full order harmonicity, right? But it still has the temperature effect. When you have a different temperature, you get.
But the potential is always the same, no? So the potential in which that determine the forces of the atoms, that potential do not depend on temperature. So if you have an exact expansion of the potential and the forces that you get from a dynamic, that doesn't depend anymore on the temperature. Only if you truncate the Taylor expansion up to a finite order, that depends on how much the molecular dynamics is sampling around your equilibrium point. So if you sample up to a different temperature, you're sampling different region of the Born-Oppenheimer energy landscape. So if you truncate the potential, so if you say I stop at fourth order, then those terms depend on the temperature because they depend on how much you're sampling. But if you have the full potential, the full up to infinite series, that will not depend on how much because it will have an infinite convergence radius around and so if you sample very little around the potential, you sample a lot, the terms of the Taylor expansion are exactly the same.
Interesting. Yeah, so I don't have a clear answer to your question. So in this case, when we use the sixth order potential, it's just to quickly kind of help us to sample the temperature we want. Like in the end, all the calculation we're presenting here is like we fit kind of truncated at the fourth order. Yeah. But I would be happy to hear your suggestions on that.
So if no more question, we can close here. And just before we finish, I want to also remind that there are some pizzas in the atrium. So you're welcome to stay and also continue discussion with Zhiting. Thank you, Zhiting.
Thank you.